Hello folks, I'm Mr. Pinola. Today I have a metal rod in front of me. I'm going to take the temperature of the metal rod roughly 2/3 of the way down at this point using my infrared thermometer. The rod is at a temperature of 21 degrees Celsius. That makes sense. It's roughly at room temperature. Now you might have noticed that I've done something different. I've put part of the metal rod in the field of this flame coming from this Bunsen burner. Now the flame is really hot and it's pointed at one part of the rod, but it's not acting on the part of the rod that we were concerned about. Remember, we took the temperature of the rod right about here. I'm going to do the same thing again with my infrared thermometer, and let's measure the temperature of the rod at this point. Again, roughly 2/3 of the way down, not the part that is in the flame. You'll notice that the temperature of that part is 22.6 degrees Celsius. It used to be 21 degrees Celsius. The temperature of this part of the rod has gone up. But this is not the part of the rod that's in the flame. The flame is on the middle part of the rod, not 2/3 of the way down where I was taking the temperature. How did the temperature of this part of the rod go up? The key here is that heat is transferring through the rod. This part of the rod that's in the flame, let's take a quick look at its temperature. It's 183.1 degrees Celsius. Super hot. That means that this is at a higher temperature than the other end of the rod. If you recall, heat always flows from high to low temperature. And that's what's happening here. Heat is flowing through the rod from this part of the rod that's at the high temperature to this part of the rod that's at the low temperature. And that heat, that energy, is flowing through the metal. It's allowing heat to get from a warmer place to a cooler place. And that's why the temperature of the end of the rod has increased, even though it's not in the flame itself. This is one form of heat transfer, and it's called conduction. Today, we're going to take a look at how conduction works and also introduce the two other types of heat transfer that allow heat to move from high to low temperature. So we know that heat is a form of energy that transfers due to a temperature difference. And you just saw one of the three methods of heat transfer. It's called conduction. More specifically, conduction is heat transfer through solids. Our metal rod was a solid object, and so heat transferred through the metal rod from one part, where the flame was, to the other part, where there was metal that was not in the flame. It works something like this. Inside our metal rod, there are lots and lots of different tiny little particles. When I heated up the particles at one end by putting them in the flame, they started moving around a little bit faster. And that makes sense because we know that when something's at a higher temperature, the molecules inside start vibrating around a bit faster. So these particles start vibrating faster. They bump into the particles next to them, their neighbors, and they start pushing on them a bit more and causing them to vibrate a bit faster. Then they bump into their neighbors and they start moving faster. And it's almost like a series of dominoes that are being knocked over. The faster particles cause their neighbors to speed up, and it causes their neighbors to speed up, until eventually all of the particles along the solid are moving faster than they were before. And so heat will eventually transfer from one end to the other. Due to the fact that the particles start vibrating faster, they bump into each other more, and they send heat all the way along the solid. Now, you may have noticed from my demonstration that I specifically picked a metal rod. Do you know why? Metal, such as this one that I drew on the board, is a good thermal conductor. A thermal conductor is something that allows heat to flow through very easily. It's due to the presence of something called free electrons. Metals are good examples of thermal conductors. They allow heat to carry all the way through them. But what if my rod was not made out of metal? What if it was made out of glass, let's say? Well, then heat might not make it all the way to the end. Sure, the particles will still vibrate faster, but something like glass doesn't have these same free electrons in there. And as a result, glass would not be considered a good thermal conductor. Instead, glass would be considered a good thermal insulator. Because heat would not be able to really travel through the glass in the same way that it would travel through the metal. Wood is also an example of a good thermal insulator that does not allow the flow of heat. What's more, plastic would also fall into that category. Anything that is a good thermal insulator does not allow a lot of heat transfer by conduction. On the contrary, things that are good thermal conductors allow heat transfer very easily through conduction. If you're a good thermal insulator, you are not a good thermal conductor. If you're a good thermal conductor, you are not a good thermal insulator. But did you know that conduction is not the only way that heat transfers from one place to another? Here I have our flame once again. It's really hot. And with me, I have two wooden skewers that have tiny little marshmallows on the end. We're going to take a camping trip to the physics classroom now. I'm going to heat up these marshmallows two different ways. One of them I'm going to put above the flame, and one of them I'm going to put on the side. If you've ever been camping and you've made s'mores, I think you can probably guess which one's going to heat up faster. Now, it's important to note that I'm not putting either marshmallow in the flame. That would be heat transfer by conduction. But neither of these marshmallows I'm going to heat by conduction. Let's have a watch. Notice that neither marshmallow is being heated by conduction. But see the marshmallow on the top? I've almost burned it. The marshmallow on the side, maybe it warmed up a little bit, but really nothing dramatic happened to it. So this marshmallow was simply above the flame, and yet it got very burnt and crispy on the outside. But the marshmallow that was next to it didn't. If neither marshmallow got heated up by conduction, then how did these two marshmallows get heated? Let's take a look. Well, it turns out that our marshmallows actually got heated by two different ways. The marshmallow that got burnt was heated by another method that starts with a C. It's called convection. A lot of folks like to say that heat rises. And while we know that heat really moves from high to low temperature, there is some truth to that statement. You might notice that anytime you have a campfire, or I have my physics campfire like I did in the classroom, we do it with a lot of air around us. And so if I were to have a flame, like I had from the Bunsen burner, it's going to heat up some air molecules that are directly above the flame. Those air molecules are going to become less dense, and they rise upwards. only to be replaced by cooler air molecules from the sides. Eventually, those really now less dense air molecules that have risen upwards cool off because they get further from the flame. And they move out to the sides to make way for hotter air molecules that are moving up. Then, as they cool off, they get more dense and they sink down once again, only to eventually be heated up again once they are above the flame. This is what's called a convection cycle, and it has to occur in a fluid. This can happen in water, where there are molecules moving around, or it can happen in a gas, like air. But if there was no air around, you couldn't heat your marshmallow up by this method. And that's because you need the air molecules to get heated up right above the flame, get hot, get less dense and rise, and then move to the sides as they cool down and become more dense. So, convection is our second method of heat transfer. And convection occurs through liquids and gases due to or because of density differences. Convection is heat transfer through liquids and gases, in other words, fluids, due to density differences. We heat up the particles that are directly above our flame or our heat source, and as a result, they become less dense, rise, and then become more dense and cool off and sink down. The end result is that heat is transferred in this case. And when I had my marshmallow above the flame, heat was transferred from directly above the flame to my marshmallow via convection. But what about my other marshmallow? It was heated up a little bit, but certainly not by convection because I didn't hold it above the flame. How was this marshmallow heated? Well, it was heated up by our third method of heat transfer, and that's radiation. Radiation is another method of heat transfer. But this occurs through electromagnetic waves. Specifically, if you paid attention during our waves unit, by IR or infrared rays, which are the heat rays on the electromagnetic spectrum. So for radiation to occur, you don't need it to go through a solid. In fact, these marshmallows were not placed in the fire, and they were not resting on a piece of metal. So there was no conduction that heated them up. They also were not heated by convection because they were not placed above for the air molecules to become hotter and less dense. So instead, heat transfer through electromagnetic waves is the way that this happens. What occurs is if you have a fire or a heat source, it gives off infrared radiation in all directions. That's why you feel warm next to a heater. And so as a result, there's going to be heat waves that radiate out in all different directions. These are the electromagnetic heat waves. And as a result, radiation is heat transfer through electromagnetic waves. You don't have to be above the fire to still feel hot because the electromagnetic waves, the infrared radiation, will still be able to travel out to you. So I hope you learned something today about the three types of heat transfer: conduction, convection, and radiation. Conduction occurs through solids, convection through liquids and gases because of temperature differences, and radiation is heat transfer through electromagnetic waves. Conduction is almost like when you touch something that's really hot, that's been in a flame. The heat will transfer through the solid to you. Convection is like when you put your hand above a flame. The hot air rises, and that's convection. And radiation is like when you stand next to an open flame, maybe next to a fireplace. You still feel warmth, and what you're feeling is the infrared heat rays that are being emitted from the heat source. Before you go, I want to ask you one last thing. Does the sun heat up Earth? Of course it does. However, you might be thinking that something seems strange about my heat transfer method. Does the sun heat up Earth through conduction? No, there's no solids that are connecting Earth and the sun. So does the sun heat up Earth by convection? No. And that's because in outer space, there's no air. And also, Earth is not sitting above the sun, so the sun doesn't heat us through convection. The sun actually heats us through radiation. Do you remember from our waves unit that electromagnetic waves can travel through outer space? That's because electromagnetic waves do not need a medium to travel. They can travel through a vacuum, and outer space is a giant vacuum, a giant area with no air. So if you get asked, how does the heat transfer from the sun to Earth? Think radiation, because there's no air in between Earth and the sun, and there's no solids.